First, we'll look at just all the review stuff from Algebra 1 for solving exponents and simplifying exponents. And then the Algebra 2 part 2 there, is really just graphing it. You'll find the graphing is probably easier than the review part we're about to do, because as I mentioned, there's 5 main rules that we use all the time. There's actually 6 listed up here, but one of them is more obvious than the other 5. So we'll just review each of these 5, do a few practice here to make sure we understand it. This chart here you can use when you're doing cube roots and fourth roots and things. So if you want to do what's the fourth root of 256, you know the answer is 4. So it's just kind of like a cheat sheet if you need it, but you may or may not, just depends. Okay, so let's look at each one of these rules just as a reminder. You probably already are familiar, but it's more difficult just to tell them apart from each other than to just know how to do them. Meaning, when you have something like this, like 2 to the second times 2 to the third, right? What's the answer here? 2 to the what? Fifth, right? And then how can you get that? Using 2 and 3. Just add them up, right? So if you have 2 bases, each with their own exponent, the bases have to be the same. So this can't be 5 to the second plus 2 to the third. It has to be 2 to the second times 2 to the third, right? Then we can add them up. It's the same idea if we just counted them up. If we just said, okay, there's 1, 2 here, and then 3, 4, 5 here. All together we have 5 total, 2 to the fifth. Notice how the base does not change. It's not 4 to the fifth. It stays the same. Okay? So that's often confused, and I'll skip over to this one where you have 2 to the second to the third power. So this is called power to a power rule. It's the same as this. If I did 2 to the second 3 times, times 2 to the second, times 2 to the second, which of course, using the first rule, if I had the same base, I can add the exponents. 2 plus 2 plus 2 is 2 to the sixth. And these two are often mixed up. When do you add them, like right here, and when do you multiply them, like we did here? Right? Because 2 times 3 can give us the 6, and we don't really have to write that part out. So you notice how here there's only one base, there's only one variable or one number, but 2 exponents. It's called power to a power. So distinguishing between these two usually makes a big difference. You know, whether you add or multiply them will change your answers dramatically. Here, where you have one on the top, one on the bottom, you know, it's less likely to confuse, but still, it helps to do these with numbers just to remember how they go. So if I had 2 to the third divided by 2 to the second, what would that equal? And if you're not sure, you can always expand, right? So that means on top we have 2 times 2 times 2. On the bottom we have 2 times 2, which means we have some canceling. So there's only 1 2 left over. So how can you get an answer of 2 to the 1 using these two numbers? Subtract them. Yes, so we have A minus B. Basically, the subtraction says we're going to cancel out that many from the top or bottom. That's what we do when we subtract it. However many we have at the bottom, these two will cancel out, so subtract it from how many there are on top. So far we have an instance where you add the exponents, where you subtract the exponents, and multiply the exponents. So you can see this is where it starts getting confusing. Not that any one of these is difficult by themselves, but mix them all together and it's like, okay, on this step, what should I do? Should I be multiplying, adding, and so on? Here we go. What about dividing when it's A over B? What do we do here? Okay, so we already kind of looked at that. If we had 2 to the 1/3, we said that's the same as actually I'll do 8 to the 1/3 just to make it solvable. If I had 8 to the 1/3, that's the same thing as the cube root of 8. So the number on the bottom here acts as what root to take it to. If we have a number on top other than 1, like let's say this was a 2 to the 2 power, it just means get that answer and raise it to the second power. So first you do the bottom number, take it to that root. Next you do the top number and just raise the answer you got to whatever power is on top. So that would be, first take that root of the bottom number. Second, raise whatever answer you get to the top number, A. Now, if you just have a number and you're raising it to another fraction, you could just put it in the calculator and it'll give you what the answer is. But you'll see in the directions it says, make sure you can do it without a calculator. It's going to be tempting just to punch it in there, but it's going to give you only decimals and not the fraction exact answer. Let's see here. What is x to the 0 power? Always debate about that. Does it equal 1? Does it equal 0? What does it equal? And if you have an answer, can you prove it? Other than, I think I remember that's what the answer is. But do you have an evidence? There's a way that you can show or explain to someone that's not here right now why your answer is correct absolutely. If not, consider doing this. Use a pattern. So, for instance, 3 to the third power is equal to 27. 3 to the second power is 9. 3 to the first power is 3. We know this, and you can use any number. You could use 2 or 4 or 5 or whatever. But look for the pattern. What's the pattern on the left? Going down by 1. So the next step here would be, what's 3 to the 0? And then follow the pattern on this side. How do we get from 27 to 9? Divide by 3. From 9 to 3? Divide by 3. So this, by doing it again, will give us for sure what 3 to the 0 should equal, because I'm just following a pattern. I'm not, well, because I believe it or because I think it, but so what we got 27 divided by 3 is 9, 9 divided by 3 is 3, 3 divided by 3 is, gives us the 1. So that means 3 to the 0 power is equal to 1. So that's the way you could prove it, not just by saying, I think it's this, or is it 0, or is it 1? I can't remember, there's a way to figure it out. And so to the 0 power, we use 1. Okay.
Wait, any number to the 0 power is 1?
Any number to the 0 power is 1 is kind of true. Kind of true. Where would it not be true? Yeah, what happens if you do 0 to the third power? What does that equal? 0. And 0 to the second power. And 0 to the first power. 0 to the first power. So according to this pattern, these are still going down by 1. So 0 to the 0 should equal. And according to this pattern, they're all zeros. So in this case, to the 0 power equals 0. So it's kind of weird when you start thinking about 0 to a power. And when you're dealing with exponents, 0 is kind of funny like that. So we kind of assume that when we're doing these problems, that the variable does not actually equal 0. And if you go back in the old math textbooks and stuff, they always put a disclaimer. For everything we're about to do, just assume the variable does not equal 0 because this rule will not apply. But the good news is, very, very rarely are you going to be raising 0 to a 0 power in mathematics. It just doesn't come up. We usually deal with the other extreme with infinity and things like that. All right, so good question. What about a negative power? So let's continue this pattern, right? So we went from 3 to 2, 2 to 1, 1 to 0. What's next in the pattern? Negative 1, right? So what's 3 to the negative 1? Don't have to guess, just follow the pattern. Divide it by 3 again. So 3 divided by 3 is 1. 1 divided by 3 is 1 over 3, 1/3, right? And then continue that pattern. Negative 2, therefore, divide that by 3, and you get 1 over 9. So you can see here that a negative exponent is a positive fraction. This is like a big concept right here. A negative exponent is not a negative number. It's kind of like like zooming in on a microscope. If you're looking at like the size of an atom, you might have seen this in science and science classes. It'll say like, oh, the size of an atom is 5.2 times 10 to the negative 17th power. Well, the negative 17th, 10 to the negative 17th power just means very, very small. It's not a negative length. It's just so small. It's microscopic. So anything that's microscopic is measured in negative exponents because it's so small. And if we're talking about the size of the galaxy, it's measured in very big exponents that are positive. Okay, so negative exponents are just very, very small things. Size of cells, size of atoms, size of whatever. They're fractions, they're microscopic. So just keep that in mind because this is going to come into play next week a whole lot of like, well, can you have a negative answer, or is that even possible? Things like that. Okay, so negative exponents, positive fractions. Okay, so those are the 6 rules. Again, this kind of middle one we don't have to really do anything. We just have to remember to the 0 power is going to be 1 always. But the other 5, you might have to refer back up to here and look at it and see, well, this particular part of the problem looks like which one of these, does it look like this? Is it a fraction exponent? Is it a, dividing 2 numbers? What does it look like? So for instance, right here on A, we have 8 to the negative 3 over 2, or negative 2 over 3. So this is really 2 different properties. We have the first property of it's a fraction exponent, so I'll definitely use this one. But then it also has a negative, so I'll have to use this property over here that says here's what you do with negative exponents. So most of the problems combine 2 or more of these together, and you have to figure out which ones. And there's going to be multiple correct ways of doing these. So your answers or your work will not necessarily match somebody else's, but the answer will. So according to this, here, the bottom number should be the root. So bottom number should be the root. So I'll make that. Okay. Top number, A, I just raised my answer to that power. So the top number here is negative 2. So I'm just going to raise whatever I get here to the negative 2 power. All right, a little bigger. So cube root of 8 once again is 2. So what's 2 to the negative 2 power? This is where you use the second one. Go back over here. All right, so negative power just means 1 over your base to the positive power. So I'm just going to make this equals to 1 over my base, but it's now to the positive power. So it's 1 over 2 to the 2. And when practical, go ahead and simplify. So 2 to the 2 power, you can do that pretty easily. So do that. If that was like 3 to the 10th power, that's a number with probably 14 digits. You don't have to write it out if it's a super duper big number. But if it's a small number, yeah, go ahead and write it out. So that's the kind of process you want to do. As you saw in Khan Academy when you started, you did this just by staring at the question and looking at it. You saw how bad that worked out. Yeah, do not try to do this just by staring at it and writing the answer down. It will not work out well for you. And this is one of those things that people, again, assume, look how small the question is. It's easy. I should be able to look at it and get the right answer and not write anything, and it'll be fine. It will not work out that way. So there's a reason why this is in Algebra 2 and not in junior high math. Okay, so keep that in mind. Lots of little details that can be overlooked. All right, give number 1 a shot. It's a little bit easier. There's no negative. So you're just using really one property. Just practicing this one right here. So what would that come out to? Go ahead and get an answer, show all the work, check with someone next to you just to verify, make sure it comes out to what you think it should be. What? 48? 64? Which one? 64? Okay, so we have the square root of 16 and raise that answer to the third power. So that's 4 to the third power, which is, of course, 4 times 4 times 4. 4 times 4 is 16, and then 16 times 4 does, give us the, 16 times 3 is 48. So very close. Lots of room for little errors, just be very careful. All right, now let's look at these two that are a little bit bigger. So these are going to use multiple properties, like 3 or more. So it helps to identify first what you're going to be doing. Don't just start on the left and work your way down or anything. Look at the whole problem and kind of analyze, well, what should be a good strategy for approaching this. You can see that we have power to a power, like right here. There's one base with 2 exponents, so at least for these two, I'm going to need to multiply them. You might notice that here there is no exponent, so what's the exponent when it's missing? Like by default, what's the exponent? Yeah, it's kind of like x, what's the coefficient of x? You always know it's a 1x. Well, the default exponent is to the 1 power as well. So if I say x, it's understood that means 1x to the first power. So if it's missing an exponent, you can put a 1 there, or just remember that it's 1 and do the problem that way. So, and then we have, what we got here? Yeah, then we have to add these together. I'm going to get this answer, whatever this is, looks like it's -6. Add that to 3, because then I'll have 2 bases, right, with 2 exponents. So I'm going to use this property twice after I do this one. But then I'm going to have a 4 to something on the top and a 4 to something on the bottom. So that means I'm going to then use this property, right? I'm going to have a 4 on top and bottom. I'll have to subtract them. So it's good to do this first, and this is the hardest part to get you guys to really do, because you want to be so eager to start writing something down. But having a plan before you start will make this so much easier. Figuring out, okay, I need to use these 3 rules, and then figuring out, okay, I need to do this one first, the yellow one first right here, then do the green one on the top and bottom, then do this pink one. Have that order all ready before you start, and these problems become a lot easier. So let's see here. So I'm not going to change anything except for the part that I set out to do in that order. So these are going to stay the same. Not going to do anything. Try to do multiple steps. All right, so this part right here, again, it's a single base, 2 exponents, single base, 2 exponents, multiply the exponents. So this is going to turn into 4 to the -6. Okay, and then next, right, I have 2 bases, 2 exponents on top. So that's what this is, 2 bases, 2 exponents, add them. And same thing the bottom, 2 bases, 2 exponents on the bottom. So I'm going to add those two together. So notice how the bases do not change. They're both 4 to some power. 3 plus -6, -3. 1 plus -2 is -1. Okay. And now I have finally this part right here. I have the same base on the top and bottom with different exponents right here. So I need to subtract those 2 exponents. So my answer will be a little bit closer. I'm going to do -3 minus, gotta be careful on this, -1. So the negative here on this -1 is not the negative here. The b value is actually negative, so that's why I'm subtracting a negative number here. And that's one of those little things, if you just stare at the Khan Academy, you tend to miss things like this. Oh, I got it wrong again. How come? Let me just guess another answer. I got it wrong again. The guessing and checking does not work so well. If you write it out, you'll see these little things and you won't make those mistakes. So now we have, what, -3 minus -1, which equals, what, -2, right? Yeah, because the Two negatives make a positive. Negative 3 plus 1 is negative 2. So we have yet the last rule. We have a negative, so that's going to be a positive fraction. So once again, just like we did up here, we had 2 to the negative 2, so that was 1 over 2 to the positive 2. We have 4 to the negative 2, so that's 1 over 4 to the positive 2. So that equals 1/16. So quite a little bit of working here. We actually ended up using 4 different properties. We had to multiply exponents, we had to add exponents top and bottom, then we had to subtract them, right? And then when we subtracted them, the answer came out to a negative exponent, so we had to do one more and take care of the negative exponent. So small problems that have a lot involved. All right, so I'll leave it for you guys. Go ahead and try number 2 here. Referring to the top, first come up with a plan. What are you going to do first? What are you going to do second? Think about the colors and the order that you're going to do them in. Don't just start writing and quickly doing it. That's what you did in Khan Academy and it did not work. So slow down and it'll probably come out a little bit better.
I also got 9.
Oh, it's got 9? Okay, let's try it out. So just like the last one, it has this power to a power. I did that first. And this also has a power to a power, right? Just on the bottom instead of the top. So it makes sense to do that first, right? Don't deviate from the order. Keep it the same. So at least I know I'll have 2 times negative 4. That'd be 3 to the negative 8. Right? And that will stay the same for now. And then I'll just do all this the same. 3 to the 5th. 3 to the negative 2. And what I just wrote down is the hardest part, the part in black. Because people tend to, well, I want to, okay, multiply those, then add those together, then I do this, and you're trying to do it all at one time. And that's where the mistake starts, because you're trying to rush through it. I want to be finished first, so I have the wrong answer, is basically your approach. The speed at which you get the answer is not helping your cause. So just do one thing at a time, even if you have to rewrite something and not change it all. Next, it's what we did in green. On the last problem, just add both of them up, right? Don't change anything. So 5 plus negative 2 plus 0 is 3. And here we have negative 8 plus 6 is negative 2. Okay. So it's looking very similar to what we had over here. We had 4 to the negative 3 over 4 to the negative 1. So since we're dividing, we have a division here. Go ahead and subtract the exponents. Watch out for this double negative, just like we already explored. So we're going to have 3 to the 3rd, and the formula has us subtracting the 2 exponents. So we're going to subtract the negative. Yeah. So this is where you could mistakenly get 3 to the 1 power if you just did 3 minus 2 instead of 3 minus a negative 2. So we have 3 to the 5th power, which equals 243. Okay. Yeah. All right. So once again, that's tricky. If the bottom number is a negative, you'll have minus a negative. Okay. But unlike the last problem, this came out to be a positive number, so we didn't have to do this one last rule and make it a fraction or anything. So one little less step compared to the last problem. But still, lots of detail, right? Slow down. Be very conscious of what order you're going in before you start. Already know, okay, I'm going to multiply these, add all those together, and then I'm going to subtract the 2 exponents, have that planned out, and then as you're doing the problem, you're just worrying about negatives and not making little mistakes. All right, let's look at just the graphing that's below. You'll find this a lot more straightforward and actually probably easier. We're going to look at domain and range and asymptotes and things like that, but we've done that more recently, so I'll probably come back to you pretty quickly. So if I'm going to raise this to the 2nd power, to the 2nd power, right? So that'd be 1/3 times 1/3, which equals 1/9. So 2 comma 1/9. Let's say this is, make this 2, it's going to be 1, -1, -2. So 2 comma 1/9. That's basically almost 0. It's a very small number right there. And then do the same thing. What if this is to the 1 power? Well, 1/3 to the 1 power would just be 1/3. So at 1, I'll have it 1/3, which is still very small, just a little bit bigger. More graphing. We have, what's 1/3 to the 0 power? Oh no, yeah, 1. So 0 comma 1, right there. What about to the -1? So what does the negative do to the fraction here? Just flips it around. So if positive 1 is 1/3, the -1 will be 3/1, or just 3. So we have -1 and 3. And then let's go orange. Lastly, you can probably see a pattern now. What would to the -2 power be? Probably 9. Yeah, and you can always put these together that it's no coincidence that this is 1/3 and this is technically 3/1. So if this is 1/9, that this should be 9/1, which is 9, and so on. So always looking for patterns. That's the nice thing with exponents, is that if you get lost, you can use a pattern to find out where you're going. So we got 3, 4, 5, 6, 7, 8. Kind of goes off the graph. There's our 9. So this is the shape of an exponential graph. We haven't graphed, exponent powers before. This is what it looks like. It kind of resembles the rational functions that we did before. Okay, those rational functions that, kind of look like this. Kind of looks like that a little bit, right? Kind of looks like we have a asymptote maybe. Okay, so a few things about this. Talk about the domain and range. The domain is over here. Are there any values of x you're not able to plug in? Can we plug in positives? Yes. Can we plug in 0? Yes. Can we plug in negatives? Yes. We don't have any like removable discontinuity or vertical asymptotes because we don't have any variables in the denominator here. So back in the day, we had like x minus 3. We would say that, oh, well, the domain is almost all reals, but x can't equal 3 because 3 minus 3 would be 0 in the denominator. You can't do that. But we don't have that in this case. Okay? X can be anything. X can be any real number. So we just use that fancy looking R for real numbers. We could say from, negative infinity to positive infinity, same thing. Now the range, looking at the graph, or looking at these numbers, are there any answers that we cannot get? Do you see this graph going below down here at all? No. And all these numbers are all the negative y's, right? This is -1, -2, -4. These are all the negative y values. So it seems that y is going to be greater than 0. It's above, right? The whole graph is above this line. It's only in the positives. How come? Well, these are all positive numbers. Can you ever get a negative answer here? By plugging in any value of x, will we ever get a negative answer? No. Positive exponents, right, give us positive answers. Negative exponents just flip the positive number. So it's, again, very important to remember, negative exponents are not negative numbers. We're not getting any negative graph down here below. It's just a very, very small number, and that's it. So here our answer is just, well, our answer is going to be anything above 0. You can't get an answer of 0, by the way, when you're dealing with exponents. Because even when you plug in 0, your answer comes out to be 1. So it's not going to, this would be incorrect. If you put equal to, it's not correct. it'll never be actually equal to 0. You can get really, really small, just like when you're measuring the size of an atom. It could be super, 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 duper, duper, duper small, but it's never going to actually measure 0 length or 0 size. Okay, so this number is going to be the same as your horizontal asymptote. So basically right here you can kind of see an asymptote where it gets closer and closer but never actually equals 0. You can get super, super small, but it will never actually equal 0. So we got y equals 0. So these numbers will always match. Our y-intercept in this case, you can see right here where it intersects at 1. The y-intercept is just where does the, when x is 0, what's the y value? That's the same question as what's the y-intercept when x is equal to 0. You can see as x increases from left to right, meaning as you go to the right, x gets bigger. You can see as you go from left to right, the y value is going down. It's getting smaller. So it's decreasing on this particular one. Decreasing. And the way we did this, I think when we were doing end behavior, we were saying things like this. Like as x goes to infinity, we did this. F of x is going to negative infinity. And it's kind of like that, only in this case, it's not negative infinity. It's actually getting closer to 0. So, but it's along the same lines. You're just thinking long term, what's happening. This is getting closer and closer to 0, but never actually gets to 0. Now, when it's actually starting at a big number and actually getting smaller, so we're starting at like, 9 here, right? And take a third of 9, divide 9 by 3, you get 3. Divide 3 by 3, you get 1. 1 divided by 3 is a third. Right? Every time we're just making a third of the size or 3 times as small is another way of saying that. 1 over 3, 3 times as big is, or 1/3, 3 times as small is the same thing as saying, take a third each time. We say if it's decreasing, that's the same thing as decaying. It decays. In your science classes, you probably seen like radioactive decay. This like radiation will decay over time. It uses an exponential function to measure that, to see how long it takes radiation to actually be absorbed. All right. Now, the way you can tell if it's decay or growing is that this number is telling you it's getting smaller because it's 1/3. But if this number is bigger than 1, that means it's getting bigger, obviously. So when you get over here, you can see, oh, this is doubling 2 times. It gets twice as big every single number. So this is going to be exponential growth. And you can tell like smaller than 1, decaying, bigger than 1, it's growing. So I really want you to look at these numbers and think not just, oh, that's 2 to the x, but that this is doubling. It's getting twice as big. Whatever you're measuring gets twice as big every time you measure it. So we have 2 to the 2 power, which is 4. 2 to the 1 power, which is 2. 2 to the 0 power, which is 1. Negative 1 to the, 2 to the negative 1 power is, and if you're not sure, if you have the positive 1 answer and you're trying to find the negative 1 answer, just do the reciprocal, right? 2 is the same as 2 over 1, so the negative 1 power will be 1 over 2. Okay? If you're trying to find the negative 2 power and you already have the positive 2 power, just do its reciprocal, so that's 1 over 4. But as you can see here, it's starting small at negative 2. It's at 1/4. At negative 1, it's at 1/2. At 0, y-intercept, it's at 1 again. And then at positive 1, we're at 2. And at positive 2, we're at 4, right? So this is kind of like somewhat of the opposite of what we just did. It's starting small, but then it starts doubling and doubling, again, bigger and bigger and bigger. We still have this horizontal asymptote. We add 0, so my range is still going to be bigger than 0. I can still plug in any numbers. I don't have to worry about point discontinuity or anything like that. My y-intercept is still positive 1. Again, these will always match. So where my range starts, that's where my asymptote is. The asymptote is what kind of creates that range. So we have y equals 0. Okay. This time, f of x, as x gets bigger, as we go from left to right, you can see the graph goes from small to big. It increases. So this is the opposite of the first one, where this is also increasing. Or decreases, I should say. Right? And but that's the earlier, when it's increasing, the word we use for that is exponential growth. So if it's decreasing, we say exponential decay. Decrease, decay, and they go together. Okay. And we're not going to use any other fancy words here. So, all right, so that will give you everything you need to know. I highly suggest doing most of the problems for tonight on the homework. You'll come across some of these, and I don't want you to avoid them simply because there's fractions involved. So if you flip over the homework here, like to number 13, I don't want you looking at this and saying, oh, wait a minute, it's a bunch of fractions. I'm not sure how to do that. It's the same idea. We have two exponents with two bases. You still just add them together. Right? And here we still have, okay, I had the same base, two different exponents, so just like before, subtract them. It's going to be 7 over 6 minus 1 over 6. And 7 minus 6 minus 1 over 6 is 6 over 6, which equals x to the 1. 6 divided by 6 is 1, which equals x. So this problem is not more difficult, doesn't take longer. Just don't avoid it because you're like, oh, I don't know how to do that one. And it's just basic arithmetic using the exact same rules, okay? We'll have today, tomorrow to work on some, but you also want to finish the Khan Academy tomorrow as well, so do not wait too long. Do not show up with, without starting this because you will not be able to finish, okay? All right.